Welcome to today's webinar. We're working on designing resilient systems, critical communications that save lives. Here's our agenda for today. We're going to start off with introductions. We're going to meet the speakers, who they are and what they do. Then we're going to go over a brief history of communications. Throughout the centuries, communications has been important. Let's look at some of the methods of communications from the past so we can better understand the present and the future. Early radio communications. Radio evolved and changed forms as technology grew. Today's systems are smarter and carry more data, but the basic principles remain the same. Software and compliance standards. How are the systems designed? What kind of training and certifications are required to perform this type of work? Define public safety communication importance. Fire, police, and emergency responders rely on resilient and clear communications. In today's world, it becomes more important every year. What is a distributed antenna system? In-building coverage is a very specialized field that keeps both the public safety responders and the people that they protect safe when emergency situations arise. Then we'll have some questions and answers. So for today, I am your primary speaker. I'm Gerald Rutherford. I'm a DAS designer and a systems technologist. I have a NICET certification. NICET is National Institute for Certification in Engineering Technologies, and I'm certified as a communications designer. This is United States certification. I also have an ETA, which is Electronics Training Association, and I'm certified as a CET senior. That's Electronics Technician Senior, and to get the senior, you have to have been in it for so many years and you have to have a very high top score. I use IBWave to design my projects. They have 3 levels of certification, 1, 2, and 3. I'm IBWave Design Certified to level 3. These are important certifications that are necessary, as a lot of places will not let you do a design unless you have these certifications. I'm certain in your section of the world, there's similar certifications that you must possess to prove that you can do a capable and qualified design. Now we're going to take a brief look at communications before electronics. Back in the Roman days, they had these towers and they set them up periodically. And what they could do is they could, if they knew a certain event was going to happen, hey, we expect that the enemy's going to be here. And then they would light that fire and put it out, and they could very quickly get that message across. It was okay for doing a single message, but more communication, more difficult message, you had to flash the lights, and they would take their shield and move their shield back and forth, which was somewhat effective. Ships at sea used a similar system with flashing lamps, and in fact, they still do. One of the advantages of that is if you have 2 ships and they're communicating back and forth with flashing lights, the enemy and so forth can't see what's going on, so they can send detailed information without the enemy knowing what it is. Then the Greeks had an interesting thing that they did. They had this big tank of water, and it had a float, and out the top there was a pole which had multiple messages written on it. So what would happen is the Greek would hold up his torch, and if you look in the back, you'll see there's another one up there. He would hold up his torch. That told him that he was ready. And then the guy up here would put his flame down and open up the water spout. So then the water would start to drain and that post would start going down. When it got to the message that he wanted, he would hold his flame up again. and the other guy at the other end would shut his water off. And that way they could read the message like, we're okay, we need help, or whatever the message happened to be. And they had several messages on there. And that was a vast improvement upon the previous systems. And in history, things keep improving.
Communications in ancient West Africa. As a young boy growing up in New York, my neighbors came from Kenya, Africa. I liked to go over to their apartment and learn about the culture. They had some interesting drums that I liked. One day I was playing around with one and the husband said, "Hey, he almost played a perfect six." I thought, how can a drum be a number? And he taught me about talking drums, how they could communicate 5 to 8 kilometers with them. And I never forgot what he taught me. In Guyana, the Akan culture uses the fantamfram, or talking drum. These could be quite large. I mean, like really large. Now, they're doing some kind of a festival here and that kind of thing, and they're vertical. In actuality, the drums would be a little bit more simplistic. They'd be horizontally mounted, pointing toward where they want the sound to go, and both drum heads would be the same height, so that the person could play the high and the low and the high and the low as they needed to communicate. Now, this started in Nigeria, went to Guyana, went to Benin, then it went to Mali, and moved across the country, and it was like their main tool for communications for centuries. And then after that, it went to Afrobeat and jazz and contemporary music, and now it's more of a festival type of a thing. I don't think they still use it for any kind of communications anymore, unless they're doing like a reenactment or something like that, or they want to show people how it works. Now, the Yoruba culture had a variable pitch drum, and this thing's pretty cool. The head has all these different strings that run down to the tail, okay? And if you were to squeeze it, it pulls the head tight. If you pull the head tight, what's going to happen? The pitch is going to go up. So this thing can actually go ahead and it can change the pitch of the drum depending on how hard you squeeze it, right? So yeah, it's really cool. They can do the whole communications with this thing, which I think is fascinating.
You see, if you squeeze on the strings, you get a very high-pitched sound, like that. If you release the strings, you get a low-pitched. So between the low and the high, you can get so many different tones, like that. Okay? And that is why you can actually talk with this instrument. Back in the days, we didn't have all the cell phones and pages and all that. We used the drums to communicate. So I want to play a little bit of that for you. But in order for you to know that you can really talk, I'm going to call my own name. My name is Kwame Ansambru. I'm going to say Kwame. So if I want to really play a song, I don't want to play a song in my native language, you may not understand. How about this song? You know that song, right?
And thank you, Kwame. So I thought I had to show that to you because it's just fascinating, and I thought it was something you'd really enjoy seeing.
Now let's go way back here to the beginnings of radio communication. Radio started with very large transmitters. I mean, hundreds of pounds. They were way too large to fit into a vehicle. So when the police needed to reach a car, for example, they sent out a message and said, hey, car number so and so, I need to talk to you. They had to go to a police box, and a police box was a special phone that was used only by the police department, and it was locked up. and it relayed back directly to the headquarters. It could go to other call boxes, so they could also arrange that, one officer could talk to another officer at a different location. But as you can see, that was not very efficient. Later, the transmitters were small enough to fit in the trunk of a vehicle, but the transmission range was not very great, perhaps a couple of kilometers at most. The radio used a single channel. Everybody on the channel could hear whoever was talking if they were close enough. But there's a problem. If they were too far away from one of the persons, they might not hear them. And when they talked, there was a chance that you would block out the other person who was talking. By today's standards, these systems were very primitive. However, they made great changes in how the police and fire departments could coordinate. Soon, the other emergency services also started to add these systems to their fleet. It wasn't long before people figured out that they needed better method to communicate as the airwaves became more and more crowded. It was determined that if frequency was paired together, a new method of transmission could be used. Two-way radio communications, individual transmit and receive channel pairs. So we got signal pairs for better communications now. Instead of a single frequency radio, it evolved to have a transmit channel and a matching receive channel. So you had a nearby town, and then you had some different town, right? And you wanted to talk back and forth. It was very possible that if you were here in the nearby town and you were trying to talk to the person in the other town, they wouldn't be able to hear it. So they have a transmitter, a big tower. And what it would do is it would listen on one channel and broadcast it on another. And then when the other person talked, he would broadcast on that listen channel, and it would broadcast it on the talk channel. So the first car goes in and he makes a transmission. It's received by the tower on the receive channel. It's transmitted out on the transmit channel at a much higher power. This allows communications over a much larger distance with more clarity. When the car that's far away responds, the tower is very high and has very sensitive electronics on it. So it hears the transmission on the receive channel very clearly. And then it retransmits the signal on the transmit tower where both cars hear and far can easily hear the communications. This is a better way to send the signals out. Modern systems still use this method. So if you've got multiple police cars in one town and multiple police cars in the other, they can all talk back and forth as though they were close to each other. This requires one radio for the police, one radio for the fire, one radio for the EMS. It's a lot of radios. Bear that in mind. It'll come out be important later. Modern radio systems can now transmit audio as digital information, which means it can be encrypted. This makes the communications private, so the person or group that's supposed to hear it can have access. This is very important in the government, military, and police units. Fire and ambulance units also use encryption to prevent agencies like the news from releasing information that's private or confidential. So if there's some politician or some actor or something like that that's got a problem, they may not want everybody to know about it. They don't want the news to be able to listen in on their communications and hear what's going on. Obviously, you don't want the bad guys with a scanner to be able to listen in to the police and say, oh, they're 2 blocks away. We still have time. So now they have digital encrypted audio, which means there's a lot more safety involved for everybody using the system, and it's a lot more private. Now we're going to talk about trunking radio systems, using a computer system to control radio traffic. So imagine this, you've got a couple of different radios, right? Radio transmitters. And what happens if one of them breaks? if it's the police, for example, now all of a sudden they don't have their communications, right? That could be a big problem. Let's look into that. We've learned that radio evolved to have a transmit channel and a receive channel as a working pair. But think about what would happen if the police radio failed. They would not have communications. The other departments would be able to talk, but the police would have a serious disadvantage. Another consideration is that one agency might be very busy, while another agency is currently just sitting there idle. The other channel would have been very useful if both agencies could somehow share that resource, especially the police department that has a broken radio right now, right? It would also mean, in the event of a failure, the calls could be routed through the functional radio and they wouldn't lose the communications. So let's take a look at the basic concept. This is a modern radio system. This is what a single modern radio transmitter looks like. It contains a power supply, a processor, receive circuits, a transmitter, and a power amplifier. It's a very powerful unit capable of between 50 to 150 watts of power. A standard portable radio, for example, is typically 2 watts, and that'll give you a comparison. Now let's look at the rack. This one is a Motorola rack, and I do a lot of work with them, but there are other vendors that are slightly different, but they do have the basic same components. That's the rack. You've got a receiver multi-coupler. When that signal comes in from the tower, this has an amplifier to amplify it up a little bit and clear it up. You've got a duplexer and mixer. You're going to have transmit circuitry and receiver circuitry. They've got to be mixed together for when it gets sent back up the tower. You have a controller. It handles, like a traffic cop, it handles the traffic between all these different units. You have a combiner. Below, you can see that there's 6 big radios, and it takes the signals from each one of those and mixes them together so they can use that single antenna up on the top of the tower. And these, of course, are the repeaters. Those are the power supplies for the repeaters. And they all connect up to the tower, and it goes up, and the radio communications go back and forth through the cable into the rack. Now, some sites have more than one rack. You can have as many as 21 channels for one system at one location. Let's look at how it works. When the radio is turned on, it looks for a control channel and it affiliates with that site. So you've got a certain number of channels at the site, and one of them is designated as a control channel, and it sends out a signal that basically says, I am system number 1234, I am here. The radio is familiar with the control channel, so it logs on and says, oh, I know what tower I'm next to. I know how to communicate with this tower. During the communications, it's no longer locked to a single channel. It's not like the police have a channel and the fire has a channel and so forth. They all share all the channels now. And what they do is they make talk groups. So let's say police might be number 200, fire might be 300, and so forth. And if you wanted to talk to the police, which was group 200, your radio would, when you keyed it up, would say, hey, I'm unit number 45680, and I want to talk to the police on talk group 200. The controller sends a command that says, okay, hey, everybody in group 200, somebody wants to talk to you now. Go to channel 3, because channel 3 wasn't being used. All of them then get the message, they get the dupe, and the user gets the dupe, and when he talks, it goes out to everybody in that group. The user hears a tone, and it's usually a dit-dit type of a tone. The other people in the talk group can then talk back and forth. When they're finished, the channel is returned to the system for another group when needed. So you have all these different resources, and the cool thing about it is if one channel is bad, the controller knows that, and it will actually contact the repair crew and say, hey, my channel number so-and-so is bad. You need to come out and fix it. Now let's look at a distributed antenna system. What is a DAS and why is it important? You probably realize that if you have a large building made out of brick, stone, and concrete, it's going to block some radio signals. If there's poor coverage in a structure, in an emergency, people may be injured or killed if the first responders can't get to them and if they cannot communicate properly. Imagine, for example, a firefighter who gets pinned under a fallen piece of the building. They can't move. It's hard to see, and there's smoke everywhere. If they do not have the ability to call for help, and if the help can't communicate, the person may lose their life. My job is to prevent that from happening. We need to design a system to prevent that from happening. So distributed antenna systems, also known as DAS. Let's start off with a building. Pretend it's some big courthouse or a school or some place that's very important to us that's going to have a lot of people in there. And when we test it, we go in there with a radio and it just does not work. We need to do something about that. Well, the first thing we do is we put in what's called a BDA. That's a bidirectional amplifier. It can take the signal from the tower, amplify it, filter it, and then send it out. And it can also take the signal from inside the building, amplify it, filter it, and send it back. But we need some other stuff to make it all work. So we run a cable up toward the roof, but we think, wait a minute, if we put an antenna out there and lightning hits nearby or something, that pulse of energy could come in and destroy our equipment. Let's put a surge protector in there to stop that from happening. Make sure it's grounded. Now, if you get a surge, it's not going to get in. Then we're going to put an antenna up on the roof. And this is not your regular antenna. You see how long it is? It directs the signal like a beam, like a flashlight beam, because we don't need it going everywhere. We need it to go to the tower. We need as much of the signal as we can to go to the tower. We also need it to be the most sensitive in the direction of the tower. We don't want a lot of radio signals from other directions getting in here. So we connect that up. Now we're going to look at the output. Well, we're going to have more than one antenna. In here, let's say we have two antennas, so we're going to need something to split that signal up. We use something called a directional coupler. They're kind of interesting because they can send a certain amount of power out one port and the remainder out the other. Imagine if you had a big gymnasium and then you had a small office. You would need more signal for that big gymnasium than you need for that little office. So we can use these to determine the correct amount and make sure it gets where it wants to be. We hook that up to the amplifier, the signal comes in. We say, okay, we're going to have one of these located in the office, one of these located in the gym. Let's wire them up. So now you've got our distributed antenna system. The user comes in and he needs to talk. Well, before he couldn't talk, remember? There's somebody outside he needs to talk to. But now the signal can go through the system, out the antenna to the site, and back to this person that we're trying to talk to. And then when they talk, the signals trace back the other way, and the person inside can hear it very well. And if we do our job properly, there's as much signal inside the building as there would be outside, almost like the building didn't exist. Now, I'm using something called IBWave. It's software that allows me to take the building and design a model of the building and then put equipment in it and test it out. Here's a diagram of a storage center that we actually built and did. And if you look up at the upper left, you'll see that blue thing. That's our tower. The signal comes into the antenna. It's a little bit different type. This one's got a big panel antenna. It's still directional, but it's another type, and it's got a little bit more power to it, and they're a little bit more expensive. Then it goes down to a mast that holds it in place, and there's some weather sealing. There's some rubber mats to keep the roof from getting torn up. some concrete blocks to hold it down, and then there's a penetration that goes in the side of the building to keep the rain out. It goes down to our lightning protector, our polyphaser. You've seen that before. It goes down to our BDA, which is going to do all the amplifications and filtering. But wait a minute. What happens if there's a power failure? That box next to it is called a BBU. That's battery backup unit. Because it's so important that if it loses power, we need to be able to communicate. And during a fire or an emergency, guess what? Power can go out, right? So now we have a backup. And then after that, you can see we've got the splitters going to all the different antennas throughout the building. And this is a fairly large building, so we needed more than just 2 antennas. When we design these, I have to make sure that everything is installed the way it's supposed to be installed. So as you can see, we've got a wall mount diagram that says I want this mounted here and that mounted there, and these are where the cables go. And then in the middle, we're showing that there's that big panel antenna on the roof and where the penetration is and where the other antennas are inside and how all that wire is going to go. And then on the far side, we show, hey, this is how that antenna outside is going to be mounted, and this is where that hole has to be for that cable to run through. So there's no mistakes. They know exactly how this thing is supposed to be installed. This is the actual building that we were designing. As you can see, if you look in the middle, there's a yellow sign that says this is where the amplifier is. We put it in the middle of the building so that when we distribute the system out, we can do it as evenly as possible. If you'll notice, there's multiple different rooms. This is a refrigeration unit. So those units at the top are all heavy steel walls with food and stuff like that inside of them that's frozen or refrigerated. So obviously with all that metal, the signal doesn't get in there very well. Also, because they're different sizes, we need different amounts of power depending on the size of each of the rooms. That's where those directional couplers come in. Now, if we lay this all out, and we're very careful and we make sure we plan it correctly, then we get good coverage everywhere we need it to be. And if you look at the guide over on the right, you'll see that we promised that we're going to cover 95% of the building, and we covered 99.8% to where we specified that we were going to do it. And you can see where the power is more powerful at the antennas and it fades out as it gets further away. If you look at that scale, when it gets to the blue and the gray and the red, that's kind of bad. But you notice I don't have any of that there because we balanced it and we've got plenty of signal throughout the whole structure. That's what this is all about, making sure that our customers have good coverage throughout the structure. Now let's take a look at what this software can really do.
When we do these designs, we make a three-dimensional model of what we're working on. So for example, here you can see what the structure looks like. All right? And the model is very, very detailed. I can actually go in and I can remove the roof, and then we can see exactly how the signal is going to behave inside of the building. And you'll see that we've got all of the different walls drawn in. We've got all of the cables and where all the antennas are. So we'll go into this and we pre-plan how everything is going to go. You can see how we've got the antennas and where they're going to point and everything. And that way, we know exactly how well this is going to work before we ever even build it. And that's what you do when you do your job right.
I wanted to thank you very much for being on today's webinar. I hope you enjoyed it. And now let's do some questions and answers and get some feedback from all of you fine people.